Have you ever wondered what time actually is, and whether it really passes the way we imagine? For most people, time is what clocks measure. Space is where everything happens. But physics shows us that this separation is just a comforting illusion. In this video, you won't just hear about space-time. You'll see how it works, and how it influences everything around us. From how GPS functions to the movement of galaxies, everything happens on this invisible stage. Space-time. The journey begins with Newton and advances to Einstein. It passes through experiments that change the history of science. You'll understand how space curves, how time slows down, and why nothing can exceed the speed of light. Space-time is strange, yes, but after today it will make much more sense. Try to imagine that space and time aren't separate entities. Instead, think of them as parts of a single reality. This union forms space-time, the fundamental foundation where everything happens. In this invisible structure, galaxies spin, atoms vibrate, and even our thoughts unfold. Every second, everything in the universe follows a trajectory within this framework. This very vision completely changes our way of understanding the world. When we look around, we see objects occupying space. We feel time passing, but our direct experience hides something deeper. According to modern physics, we're immersed in a four-dimensional environment. That's 3 spatial dimensions and 1 temporal. This idea takes us beyond common perception and brings us closer to a more complete understanding. Space-time isn't just a mathematical concept. It's real and can be measured, tested, and even deformed. Consider that you're standing still in a room. You're occupying a point in space, but you're also at a specific instant in time. Together, these 2 pieces of data define your position in space-time. This very point isn't fixed. With each breath, you follow a world line, a continuous trajectory in the invisible structure. It's this kind of thinking that opens the way for us to understand phenomena like time dilation and gravity as curvature. And the best part is that all of this starts to make sense when we connect space and time in an integrated way. For a long time, physics viewed the universe as a great predictable machine. Isaac Newton saw space as something fixed and unchanging. Time, absolute, flowed the same way for all observers. This vision worked well to explain everything from the movement of an apple to the trajectory of planets. The universe was like a rigid stage, with a universal clock marking time equally for everything and everyone. But this very structure, apparently perfect, began to show flaws as science advanced. In the 19th century, electromagnetism revealed problems in the classical view, phenomena that didn't fit Newton's rules. Something fundamental didn't match the observations. Experiments of the era failed to confirm classical expectations, like the famous Michelson-Morley experiment in 1887. These results completely questioned absolute space and time. Want to better understand the speed of light? We have a video dedicated to the topic. The link is below in the description. To solve this dilemma, Einstein proposed a radical solution. If certain properties were constant, space and time couldn't be absolute. In other words, time could pass differently depending on the observer's motion, and distances could shorten when measured by someone at high speed. Special relativity was born there, a theory that would forever change our understanding of reality. Einstein showed that time slows down for objects moving very fast, and that space can suffer contraction under these conditions. The effects, called time dilation and spatial contraction, aren't just theoretical ideas. They've been measured in experiments with particles and satellites. What seemed impossible became part of the new physics. But a language was missing that would unify all of this in a clearer way. At this crucial moment, Hermann Minkowski entered the scene, a mathematician who thought beyond traditional geometry. In 1908, Minkowski presented a revolutionary vision. He unified space and time into a single 4-dimensional structure. The concept of space-time was officially born. According to him, events don't just happen in a place. They happen at a specific point in space and at a specific instant in time. Furthermore, the notion of now ceased to be universal. What is present for one person can be past or future for another, depending on their speed and position. Simultaneity became relative, and the discovery was a shock to our intuition. One of the most powerful ideas in modern physics is treating time as a dimension, in the same way as height, width, and depth. To do this, we use universal constants as a bridge between the different dimensions. This makes it possible to represent time in spatial graphs. With this approach, events in the universe can be drawn in diagrams. The time axis adds to the spatial axis. This type of representation helps visualize relationships that would be difficult to understand with words alone. In this context, the concept of spacetime interval emerges. It's the measure between two events in spacetime, considering not only distance, but also the time between them. The formula is based on Minkowski geometry. It shows that space and time mix in a unique way. If an object moves more in space, it advances less in time. And if it remains still in space, it travels the maximum possible in time. This explains, for example, why time passes more slowly for an astronaut traveling at extreme speeds. We can think of spacetime as a great stretched fabric, where each line represents the trajectory of an object. These trajectories are called world lines. Each person, planet, or particle has its own line, which shows how it moves in space and time. When two lines cross, we have an encounter. When a line is more inclined, this indicates high speed. This very visualization not only facilitates understanding of relativity, but also shows how space and time are inseparable. Together, they form the stage where everything happens. Visualize an isolated event in space-time, like turning on a flashlight in complete darkness. The emitted light spreads in all directions, creating a cone-shaped boundary. The cone represents all the points that can be reached by light, starting from that event. It's what we call the future light cone. Everything that's inside it can be influenced by the emitted light. What's outside remains inaccessible, as if it belonged to a separate reality. The concept also applies to the past. The past light cone represents all the events that could have influenced that specific point in spacetime. An example: a distant explosion may have emitted light that is now arriving to you. If it's within the light cone of the present, there's a causal connection. These cones delimit the structure of the universe in terms of cause and effect. Nothing outside the cone can affect or be affected by that event. Not even something hypothetical that moves faster than light. This leads us to a profound conclusion about the structure of reality. Spacetime doesn't allow anything to happen anywhere. There's an order governed by the speed of light as a universal limit. This preserves causality and avoids paradoxes. When scientists build cosmological models or simulate black holes, light cones help predict what can or cannot interact. Visualizing these cones shows us that the universe has well-defined rules, and that the present is just a small slice between the past that shaped us and the future that's yet to come. Starting in 1915, Albert Einstein took an even bolder step with general relativity. He proposed that gravity isn't a force like others, but a curvature in spacetime. Instead of pulling objects, large masses deform the space-time fabric around them. It's like placing a bowling ball on a stretched sheet. Smaller objects roll toward the ball not because they're pulled, but because they follow the curved path. This new way of seeing gravity completely changed cosmology. The theory predicted phenomena that previously seemed impossible. One example is black holes, regions of space-time so curved that nothing can escape, not even light. Another example is gravitational waves, ripples in the fabric, caused by extreme events like collisions between black holes. The waves were predicted by Einstein and confirmed only a century later in 2015. They're like cosmic echoes, crossing the universe and giving us clues about distant events. They confirm that space-time is dynamic and can vibrate like the surface of a lake. Surprisingly, even everyday technologies depend on the theory. GPS satellites are an example. They need relativistic corrections to work correctly. That's because time passes differently for them in orbit than for us here on Earth. The difference might seem small, but without this adjustment, the provided location would be off by several meters. All of this shows that space-time isn't just an abstraction. It directly influences modern life and our ability to navigate, predict, and understand the world around us. When we think about the universe, we tend to trust our senses. We see space as something fixed and feel time as a line that advances. But space-time reveals that reality is much more complex than it seems. It forces us to abandon the idea that time is the same for everyone. It shows that past, present, and future are relative, and that everything in the universe is intertwined by an invisible fabric that shapes events. Spacetime isn't just in books, but in every second of our daily lives. It's in the gravity we feel, in the functioning of satellites, and even in the most advanced technologies. Understanding this brings us closer to a more realistic and powerful vision of the universe. And perhaps the most fascinating thing is realizing that we're only at the beginning. With each discovery, new questions arise. What lies beyond space-time? Would it be possible to travel through time? How do black holes arise, and what exists inside them? Physics continues exploring these mysteries. And the more we learn, the more we realize that reality is much stranger and more wonderful than any fiction. Now that you know the fundamentals, you're ready to continue the journey with a new perspective. After what we've explored, an important question lingers. How much of reality do you really understand? Now that you know the fundamentals of space-time, can you still see the world the same way? Or do you perceive that the universe is more surprising than you imagined? Maybe it's time to rethink how you face the passing of time. What seems ordinary, like a fall or a second, might hide profound secrets. And understanding these phenomena isn't just fascinating. It can also change your relationship with the world. If you've made it this far, it's a sign that you have curiosity and an open mind. So take advantage of this impulse, subscribe to the channel, and activate notifications. We have many other contents like this one that will challenge your perception and expand your understanding of reality. Because knowledge is just the beginning.